Hey there, everybody. Welcome back. We are now on to our fifth and final lesson on circular motion and gravitation. And what we're going to talk about in this lesson is all about energy. And mostly we're going to talk about potential energy and how it relates to satellites or really anything that's going to be moving large distances with respect to the planet that they're starting on. And so, we've already talked about gravitational potential energy previously, and we know that EP from previous physics courses, EP equals mgh. And that's great, that works, except the problem is this thing right here. This is not constant. Now, if we're talking about being near the surface of the Earth and roller coasters and ski hills and all that sort of stuff, we can assume G is right around 9.8. But if we start moving large distances, like taking a satellite from the surface of the Earth and putting it up into orbit, then that G value is not going to stay constant over that whole time. So if you think about it, if you want to do work to lift a satellite into space, it's actually going to get easier and easier to lift it the further you go. And so G is not a constant. G depends on really the mass of and distance to a planet. And I say planet, but really I mean any body that's capable of generating a gravitational field. So planet, moon, star, whatever you like. Okay, so we're going to do a quick derivation here, which is not going to be 100% correct. And some of you might be screaming into your computer screen saying, hey, that's a little bit of cheating. But to do the proper derivation, we would have to use calculus, and I don't want to get into that right now. So we're going to use a little bit of a cheater method. And so imagine we've got this satellite, and we want to move it up into orbit. And instead of starting on a planet, imagine that I've got a very, very, very tiny, very, very dense planet. And so this little tiny planet, you could think of it as like a little mini black hole maybe. And we're going to take this satellite and we're going to move it out into space. And so we're going to start here and we want to move it a certain distance away. We want to lift it up in the air. Well, you could talk about the work that you would do on that satellite being a change in potential energy, and a change in energy is equal to force times distance. But in this particular case, you might think we start with zero potential energy, so the potential energy that we end up with would just be force times distance. And if we lift this at a constant velocity, then the force we would need to exert would just be equal to gravity. So the potential energy gained here is going to be force of gravity times distance. Now, we know that force of gravity is G times m1 times m2 over r squared all times d. And if we go back to our original situation here, because we talked about distance lifted from this single point being d, you'll notice that this is also equal to our separation distance r. So d really is the same as r, and so what happens is this d is going to cancel out with one of those r's because they're the same value. And so what we get is we get a value for potential energy, or an equation for potential energy, that is G times m1 times m2 all divided by r. Except, and this is a big except there's a negative sign in front of this whole thing. So potential energy is actually negative gmm over r. And to really properly show where that negative sign comes from, you probably have to do a little bit of calculus, and that'd be super interesting for those of you that are going to go on to do calculus to come back and go, wait a second, what happens when we do an integral here of force with respect to distance? But for right now, we're just going to leave it at that. Let's think about this negative sign though, because it has to kind of make sense. Otherwise, we're not really going to be able to use it properly. So there is a negative sign in front of that, and it comes down to the fact that whenever we talk about a potential energy, a gravitational potential energy, we always measure it relative to some reference point. And that's the reference point where we think that our potential energy has a value of 0. So you might think about problems you solved with like roller coasters, and you could think of, well, maybe the ground is 0 potential energy, or maybe the bottom of the hill is potential energy equal to 0, or maybe the top of the hill is potential energy equal to 0. Whatever you want to choose is fine. But in the case of traveling sort of large distances, we're all going to choose the same distance as being our 0 point, as being our reference point. And so we are all going to agree that our reference point is going to be where r equals infinity. And that's kind of strange. But we're going to say, listen, the potential energy is 0 at infinity. And what happens is if you are anywhere closer than infinitely far away, then your potential energy is just some negative value. So the closer you get to Earth, the larger a negative number your potential energy becomes. And we'll see that this ends up kind of making sense. Because if the furthest away you can get, being infinity, is where you have 0 potential energy, then anything closer than that would be a larger and larger negative number. And that makes sense because if you're falling towards Earth from an infinite distance away, then as you fall closer to Earth, you are actually losing potential energy. And a negative number is less than 0. Maybe another way to visualize this is to think about a sketch of potential energy versus separation radius r. Since we know that EP varies with negative 1 over r, what we would do is we would get this inverse function that looks kind of like this. And we'd see that we've got an asymptote here that as we head off towards an infinite r, eventually this function here is going to approach 0 potential energy. And anything closer than infinitely far away is going to have a greater and greater negative potential energy. I guess you could also have an asymptote here on your y-axis where this is kind of heading towards infinite potential, negative potential energy. And that might seem kind of strange until we realize that as you get closer and closer to a planet, there is going to be some point that we might call R0, where eventually you're going to hit the surface of the planet or the sun or the whatever it is. And so this would be the radius of the planet. And I keep saying planet, but I mean anything that's creating that gravitational field. So really, as you get closer to the planet, eventually you would hit the surface, and then that would be the max or the minimum, the lowest possible potential energy value that you could have. Okay, let's do a bunch of calculations and just see how this pans out. So a satellite is in orbit 3.6 times 10 to the 7 meters above Earth's surface. So let's just be really clear about that. Above Earth's surface. So I've got a satellite, and there's my little satellite. Now I'm given this distance here, 3.60 times 10 to the 7. You will remember from your data sheet that the radius of the Earth is 6.38 times 10 to the 6 meters. And so we would have to add those in to find our total separation distance. All right, so the potential energy of this satellite is going to equal negative g m1 m2 all over r, which is negative 6.67 times 10 to the negative 11 times the mass of the Earth, 5.98 times 10 to the 24, times the mass of the satellite, 2,500, all divided by the radius, which I guess would be those two things added up, 6.38 times 10 to the 6, plus 3.6 times 10 to the 7, and don't square it. I almost squared it there. Don't do that. Okay, so just putting this in, and isn't this fun, watching me type things into a calculator in a really long-winded fashion. 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 times 2,500 divided by, and I'll just add these things up, 6.38 exponent 6 plus 3.6 exponent 7, close the bracket, hit enter, and I get negative 2.35 times 10 to the 10. Negative 2.35 times 10 to the 10 joules. Now, that's kind of a hard number to know if it's right or not. Like often in physics, we always want to ask ourselves, is that a reasonable answer? And I don't know. I don't know offhand what kind of energy a satellite has just way away from the Earth. But we'll see in a second, there is kind of a way to check it. One thing that makes sense to me is that the potential energy relative to this infinite position is negative. And that's what we would expect. Because if we're closer than infinity, our potential energy should be a negative number. One way to think about that is, so flip that on its head. Why is our potential energy negative? Well, this is basically saying that you've got an energy deficit. If you wanted that satellite to completely break free of Earth's gravitational field, you would need to do more work. Well, how much more work? As it turns out, this much more work. You're basically 2 0.35 times 10 to the 10 joules short of completely breaking free of Earth's gravitational pull. So let's look at this next question. It says, okay, so what is the total energy of the satellite in this last question? So total energy. Now, if we think about it, if we have a satellite that's up in space, then we know that it obviously has potential energy. Sounds good. But if that satellite only has potential energy and isn't moving, for example, then that's not a satellite. That is soon to be a meteorite crashing into the Earth. So not only is it up away from the surface, but it also is moving. And so it must have kinetic energy. And so the total energy of the satellite is going to be the potential energy plus the kinetic energy. Now, before you go ahead and solve this, I want you to just think for a second, okay, will the total energy of the satellite be a positive number, a negative number, or maybe will it be zero? Like, what would it mean if the total energy of the satellite was positive or negative or zero? And so in this case, when we're in a stable orbit around the Earth, a stable circular orbit, let's say, what would we expect the total energy to be? Okay, so think about that as we do this question. And so maybe this would be a good time to just go ahead and pause the video and see if you can solve this on your own, and then unpause the video and then see how you did. So we know that kinetic energy is 1/2 mv squared. So if I could just find the velocity of this satellite, then I should be able to find the kinetic energy. And we also know that if we have a satellite in stable orbit, that the centripetal acceleration is going to equal the acceleration due to gravity. And so for a given velocity, v squared over r is going to equal g m1 over r squared. And I can cancel out my r value. And I can solve for v. And so v is going to equal the square root of g m1 over r. So square root 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24, all divided by, and I kind of had that messy radius, didn't I? What was that? I guess I could just write that, I could just add those up, and that would be 4.238 times 10 to the 7. Will save me a little step there in my calculator. So let's see what I get. 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 divided by 4.23 times 10 to the 7, and get that answer. And of course, don't forget to take the square root. That's looking suspiciously close to the speed of light there, and I get 3070 meters per second. Now, hopefully by now you're starting to get the sense that, Earth satellites, obviously how close they are is going to change their speed, but these Earth satellites have to travel on the order of kilometers per second, so thousands of meters per second. And so I get that as an answer, and that at least kind of reminds me of some of the other satellite questions I solved, so I feel like I'm on the right track. If I go ahead and plug that value in here for my kinetic energy, let's see what we get. So 0.5 times 2500 times 3070, and don't forget to square that. I didn't write that down, but I get 1.178, so that should be squared. 1.178 times 10 to the 10. So now I can bring it all together and I can find my total. So I had negative 2.35 times 10 to the 10 plus 1.178 times 10 to the 10 and I know it's times 10 to the 10, so I'm just going to add up. I'm not going to bother with the exponents. And so I get negative 1.17. Negative 1.17 times 10 to the 10 joules is my total energy. Okay, so there's a couple of things I want you to get from that answer. And the first thing that I hope you notice is that the total energy is negative. And so if you made that prediction, give yourself a high five. It makes sense that if this satellite is trapped in stable orbit, so remember an orbit means it's trapped there. It's never going to escape. It makes sense that the total energy is negative. If the total energy was zero, think about that. If it had so much kinetic energy that when you added it to the potential energy, its total energy was zero, then you're essentially saying that this satellite has enough energy to go to infinity. And that's what it would do. So a satellite that is trapped in a stable orbit is going to still have an overall negative total energy. The other thing you might notice if you look really closely here is that the total energy value, if you look really closely at the total energy value, you might see that this has a relationship to that. And it kind of has a relationship to this too. It kind of looks to me like the total energy value is right around half of the potential energy value. Now, it may not be exactly half just because of the way I rounded it off with sig figs and all that fun stuff. But as it turns out, that is true. Whenever you have a satellite in stable orbit, the total energy is going to equal half of the potential energy. So let's see why that is. Well, we know that kinetic energy equals 1/2 mv squared. And in the case where we had a satellite, AC equals G, which means V squared over R equals G m over R squared. Well, if I just solve this, not for V, but just solve it for V squared, I could cancel out an R and cancel out an R. And I'm just going to leave it as V squared for a moment and say that, okay, V squared equals G m over R. Now notice that that kinetic energy is 1/2 mv squared. So I could take this thing here and I could substitute it in there for v squared. And I would get kinetic energy is equal to 1/2 m gm over r, which if I rewrite it is just 1/2 gmm over r. Now just cleaning up a little bit here, because I got a little bit sloppy, but just cleaning up, I can see that m here, this is mass 2. That's the mass of the satellite. And this is mass 1. So really, this should be gm1m2 over r. And you notice that that is equal to half of gmm over r, which is really 1/2 of the negative of rep. So the kinetic energy is going to be a positive value, but if I know my potential energy value and I take the positive or multiply it by -1, half of that number will be the value for my kinetic energy.